Okay, great. This is actually not going to be so much about causal inference or about learning much at all, but about causal representation. So this is work with Delegar Ibling, and I'm the second author here. And one way to get into this topic is to think about kind of ordinary human causal knowledge. So imagine the following kind of scenario. If I, for example, have 2 cups of sand, and I'm pouring these cups of sand on the table, compare that to a situation where I have 2 cups of water, and I'm pouring these cups of water on the table. We all readily infer that in the first case, I'll end up with 2 heaps of sand, and in the second case, I'll end up with just a puddle of water. And in fact, 5-month-old infants are quite sensitive to this kind of distinction and to this kind of physical kind of causal knowledge. And it, of course, goes well beyond sand and water to include other types of intuitive physical kind of knowledge. For example, blocks. If I see a bunch of blocks piled up, I can make quite systematic and diverse kind of inferences about what's going to happen, whether they're going to fall or how stable they are, and so on. So there's a bunch of work, especially in cognitive science, but also in recent AI, that's tried to kind of formalize this kind of knowledge in terms of certain kinds of implicit kind of causal models. So using notions like physics engines or probabilistic programs to actually encode what we know about these kinds of situations in a kind of implicit way, in the sense that I can take some starting point and unravel through simulation what will happen, and the causal knowledge is somehow implicit in that simulation. So a couple of things to notice about this type of representation. One is that it is implicit. Another is that it's kind of open universe in a certain sense. Namely, I don't have to assume at the get-go, for example, how many objects I have, what the identities of the objects are, and so on. It's quite sort of schematic and abstract. But nonetheless, it seems like there is some sort of causal representation indeed implicit in these types of models. And so we want to understand that a little bit better. So in the background are kind of 2 themes. One, open universe models of a sort that are familiar by now from work in statistical relational modeling, probabilistic programming, and other kinds of related approaches that deal with situations with unknown numbers of objects, unknown identities of objects, and so on. And second of all, causal representation reasoning, and in particular I have in mind the kind of rigorous axiomatic kind of approach to this that's also very familiar in this conference. And so what we want to do in this project and what we do in this paper is try to formulate axiomatic foundations for open universe causal reasoning. So try to understand these kind of open universe types of models, things like probabilistic programs, from a causal perspective, understanding how they relate to more traditional familiar causal representations. Okay, there's a long line of work on axiomatic foundations of structural equation models, and we're going to be building on that, extending it to the infinite open universe setting. Okay, so just to kind of review structural causal models, structural equation models, we have some exogenous variables and endogenous variables, structural equations characterizing causal relationships. An intervention here, the critical kind of causal notion, is defined as in terms of equation replacement. So if I want to intervene to set some variable to some value, I take the equation for that variable and I just replace it with the value, the constant. And that actually gives rise to a notion of conditional. And in some sense, structural equation models just are encodings, succinct encodings of complex patterns of conditionals. And so we're going to write these conditionals in the following way, from more logic notation, but equivalent to more statistical kind of notation, which say things like if alpha were the case, if alpha were true or made true by an intervention, then beta would occur, or beta would be true. And we don't want this just to be settings of variables, but possibly kind of logically complex interventions and consequence there. So these causal conditionals are kind of the workhorse of most of causal reasoning. And in the finitary setting, you can actually define other kinds of notions, like that a variable causally influences another variable, where this means basically there's some setting of variables such that if I toggle by an intervention the value of x, that changes the distribution on y. So I can encode a notion of x influencing the variable y. And now axiomatizations are basically axiomatizations of these types of formulas. What kinds of counterfactual, causal kind of patterns can we encode and kind of come out as valid in these models? So without going into any details here, I just want to mention some of the classic results here, that the kind of core principles for structural equation models are written here in maybe a little bit less familiar notation, but are equivalent to the notation in these papers mentioned there. I'm not going to go through these in any detail, like I said, but suffice it to say that things like composition are actually critically used for a number of different tasks, for example, in justifying certain kinds of identifiability, algorithms showing that they're correct, and so on and so forth. So these are really core causal principles that play a role in many different settings and are arguably kind of definitional of causal relationships and causal types of encoding. So what's the alternative type of model that we want to consider now? Not structural equation models, but so-called simulation models, things like probabilistic programs. And we want to look at this at a sufficient level of generality. So we're going to take a kind of abstract notion of computation, something like a Turing machine, and we're going to have a distinguished variable tape that's going to encode the values of all of our variables. And then we're going to define a different notion of intervention, not equation replacement, but a different notion, which is to say that we go in and basically intervene on the program to block rewrites to that variable. So we go in and write the value of the variable that we want, and then whenever the program would rewrite that variable, we block it. And that's going to have various kinds of side effects on the working of the program. So there's many different examples of this kind of idea that have actually been explored in the literature. Going back all the way to the early 90s, late 80s, people have explored this kind of idea of formalizing conditionals in different kinds of neural networks. And more recently in probabilistic programs, currently there are a number of labs that are exploring implementing something like Pearl's do operator, something like the thing that we defined on the previous slide, to try to encode notions of counterfactuals and so on in probabilistic programs. So we want to understand the kind of foundations of this kind of approach. So just to give a simple, maybe a very simple example, the simplest kind of interesting example of an open universe kind of simulation program, imagine something like a very basic Chinese restaurant process where I'm generating an infinite partition, or partition on the natural numbers, and at stage n, I choose a category with probability given by the size of that category over n, and then I generate a new category with 1 over n. Suppose I end up doing something like this, assign 1 to A, 2 to B, and so on. The thing I want to point out about this process like this is that it encodes a whole bunch of causal information, interesting kind of causal information. For example, given what in fact happened here in this generative procedure, I can say, for example, that 7 joined B in some sense because 3 joined B, or at any rate, 3 was a kind of probabilistic difference maker for 7. And that can be made somewhat precise by basically encoding certain kind of counterfactual facts. So, for example, had 3 joined a different category, say C, then 7 would have been less likely to join B, for instance. So we can say, given the categories that 1, 2, and 3 in fact took, 7 had a fairly high probability of joining this category B. But if instead we had, for example, set 3 to category C, then it would have been lower, for example. And we can also do genuine kind of counterfactuals in this kind of setting, even with this very simple little generative model, for example, that is at the highest level of the kind of causal hierarchy. We can say, suppose I just observe that 3, 5, and 7 share a category. Then I can ask, well, what would have happened, given this partial knowledge, what would have happened if, for example, 5 had taken up a different category from 3? So we can actually compute that and say what the probability would have been, even given this sort of partial knowledge. So what I'm essentially doing is conditioning on this observation and then going back and intervening in the program and then running the program back forward and then letting that determine the probability of, in this case, 7 joining the same category as 3. Okay, and there are other kinds of actual models that people have proposed, not infinite going forward, but for example, considering situations where you want infinitely many possible causes. So if I'm trying to infer what the causes of some observed events are, I might want to do this using some sort of similar non-parametric generative model that could possibly, that has a kind of unbounded number of causes in the first step. And this kind of thing has been explored. So it looks like from all these examples, this is just another way of talking about familiar kind of causal models, right? It's just maybe a notational variant of structural equation models. But one thing we noticed this is from a paper last year, is that actually this interpretation is quite different from the notion of intervention in a structural equation model. And I don't necessarily intend for you to read all of these axioms, but we actually gave a complete axiomatization of programs with this interpretation. And the bottom line is basically that the system is very weak. And it doesn't validate any of these principles that I mentioned a few slides back that are characteristic of causal conditionals, in particular the kinds that play into standard causal reasoning. So it looks like this kind of program model with the notion of intervention on the program is actually not necessarily, it's not necessarily possible to give that a causal interpretation. So that just invites the question of whether we can find subclasses of these two types of causal models that actually do coincide, that actually do agree, and can be thought of as genuine notational variants of one another. So in that direction, we consider a subclass of simulation programs, essentially with the following kind of characteristic. If you want to see more details, it's in the paper. But we assume that basically causal influence within the program, so one variable causally influencing another within the program, has to be in a certain sense acyclic and well-founded. So it's sort of respecting a kind of temporal structure. And then one more kind of technical constraint that we have on interventions. And we also actually need to constrain the class of structural equation models. So now we're in this infinite variable kind of setting. And what we need to do is assume that these are essentially kind of like recursive structural equation models. So they're acyclic, but we need something a little bit more general for the infinitary setting. So it has to be well-founded as well. And second of all, the structural equations need to be computable in order for this equivalence to go through. And this kind of computability assumption has been considered before in the literature. And here, if we make that assumption, then we can show that these two classes are genuinely expressively equivalent. What does that mean? If I take a computable structural equation model and I consider all of the counterfactual and hypothetical predictions that it makes, I can find some simulation program in this class that makes exactly the same pattern of predictions, okay, and vice versa. So they're really genuinely notational variants of one another and can be used for all the same kinds of purposes, at least in principle. So then it's probably not surprising that we could just write, for example, the Chinese restaurant process as a simple little structural equation model, and all of those counterfactual claims that I gave before can be derived just in the usual kind of way with structural equation models. Okay, so the further work that I'm not going to go into detail here about is that we can actually axiomatize these classes of models, which turn out to have the same axiomatization being equivalent. And it's really just a kind of conservative extension of the traditional setup with finitely many variables in the closed world setting. And in particular, it's the system that I showed a couple of slides earlier, together with those rules from the earlier slides of composition and recursiveness. So it's really a kind of conservative extension of classical kind of reasoning, but now in this kind of infinitary setting. Moreover, in the infinitary setting, we can actually consider types of operators and relations that were kind of trivialized in the finitary setting. So things like causal influence, which were actually definable in the finitary setting, are no longer definable, but we can characterize, for example, interesting classes of causal models using this further relation. So for example, if I assume causal influence is transitive, this characterizes exactly those causal models, either structural equation models or programs, in which causal influence is kind of immediate, that with this implicit temporal ordering, I don't need to go back further back than the previous time point. Moreover, I should just mention that all of these systems remain of relatively low complexity, so they augment propositional logic, but they're still NP complete satisfiability problems. So the kind of abstract reasoning about these things is no more complex than in the simple finitary setting. Okay, so just to conclude, structural equation models and simulation programs, probabilistic programs of this sort with this notion of defined intervention are not in general compatible. They give rise to quite different kinds of patterns of conditionals. And in particular, it's not obvious how simulation programs can actually be given a causal interpretation that agrees with, for example, structural equation models. But they can be made to do so in a reasonably natural way. Moreover, this kind of open universe causal reasoning does admit of simple axiomatizations, just like in the finitary setting. And the broader kind of project here is to try to formalize and axiomatize even more of causal reasoning, not just conditionals and causal influence, but something more in the direction of full due calculus, so as to put this into an explicit logical calculus where we can kind of explore what precise sort of representational assumptions are necessary to get those inferences going. And of course, we want this to be appropriate for these kinds of open universe types of situations that are becoming increasingly popular as well, hence the present work. So thank you for listening.